This is Euclid Book 10, proposition number 112, and this is by far one of the longest proofs you will ever hear, because it starts off with something else and then leads into this. The apotome and the irrational straight lines following it are neither the same with the medial straight line nor with one another. For the square on a medial straight line, if applied to a rational straight line, produces as breadth a straight line rational and incommensurable in length with that to which it is applied. This is by Euclid Book 10, proposition number 22. Now this basically, at this point, is a review of all those proofs that we did so long ago. So if you want to refer back to Euclid Book 10, proposition number 22, you may do so. And you'll hear this all the time through this, okay? While the square on an apotome, if applied to a rational straight line, produces as breadth a first apotome. This is by Euclid Book 10, proposition number 97. The square on a first apotome of a medial straight line, if applied to a rational straight line, produces as breadth a second apotome. This is by Euclid Book 10, proposition number 98. The square on a second apotome of a medial straight line, if applied to a rational straight line, produces as breadth a third apotome. And this is by Euclid Book 10, proposition number 99. So if you went back to Euclid Book 10, proposition number 99, you would find this out. The square on a minor straight line, if applied to a rational straight line, produces as breadth a fourth apotome. And this is by Euclid Book 10, proposition number 100. The square on the straight line, which produces with a rational area a medial whole, if applied to a rational straight line, produces as breadth a fifth apotome. This is by Euclid Book 10, proposition number 101. And the square on the straight line, which produces with a medial area a medial whole, if applied to a rational straight line, produces as breadth a sixth apotome. This is by Euclid Book 10, proposition number 102. Since then the said breadths differ from the first and from one another, from the first because it is rational, and from one another since they are not the same in order, it is clear that the irrational straight lines themselves also differ from one another. And since the apotome has been proved not to be the same as the binomial straight line, which is by Euclid Book 10, proposition number 111, which we just did one proof ago, but if applied to a rational straight line, the straight lines following the apotome produce, as breadths, each according to its own order, apotomes, and those following the binomial straight lines themselves also, according to their order, produce the binomial's breadths. Therefore, those following the apotomes are different, and those following the binomial straight line are different, so that there are, in order, 13 irrational straight lines in all. Medial, binomial, first bimedial, second bimedial, major, side of a rational plus a medial area, side of the sum of two medial areas, an apotome, a first apotome of a medial straight line, a second apotome of a medial straight line, a minor, producing with a rational area a medial whole, producing with a medial area a medial whole. Now all these notes are very necessary because of what we're going to prove in Euclid Book 10, proposition number 112. Now let me read you the actual proof. The square on a rational straight line applied to the binomial straight line produces as breadth an apotome, the terms of which are commensurable with the terms of the binomial, and moreover in the same ratio, and further, the apotome so arising will have the same order as the binomial straight line. Confused yet? Okay. We're going to let A be a rational straight line. This is rational right across here. We're going to let BC be a binomial straight line. And we're going to let DC be the greater term. Okay, what is DC? That's right across here. It's going to be greater than BD. Now we're going to construct a rectangle. Two sides of that rectangle are going to be the length of BC. The other two sides are going to be the length of EF. That's this rectangle right here. Okay. And this area is going to be equal to the square on A. Now, what did we do about the square on A? We took the line A, we turned it into a square, and all four sides of this square are going to be the length of A. So this area equals this one. Now we're going to try to say that EF is an apotome. Now we're going to try to prove that this is an apotome. The terms of which are commensurable with CD and DB. Okay, so EF is going to be commensurable with CD. And EF is also going to be commensurable with BD. And they're going to be in the same ratio. Okay. So in other words, as EF is to CD, so EF will be to BD. And further, EF will have the same order as BC. Okay, so this is going to have the same order as this. Okay. For again, let the rectangle BD and G. Okay, so now we're going to have to form a rectangle, two sides of which are going to be the length of BD. The other two sides are going to be the length of G. And this area in here is going to be equal to that. Since the rectangle BCEF, which is this one right here, has the same area as this one right over here, therefore, as BC is to BD, so is G is to EF. That's by Euclid Book 6, proposition number 16. But this line right across here is greater than size than this line right across here. We know this. Therefore, G is a longer line than EF. Okay, this is by Euclid Book 5, proposition number 16, and Euclid Book 5, proposition number 14. So, now we're going to have a length called EH. It's going to go from here to here. And this length is going to be equal to G. Therefore, as BC is to BD, so is EH going to be to EF. Therefore, separando, as CD is to BD, so is HF to FE. Okay, so as this is to this, so is this is to this. This is by Euclid Book 5, proposition number 17. Let it be contrived that, as HF is to FE, as this is to this, so is FK to KE. So as this is to this. So as this is to this, so as this is to that. No, I'm wrong. So as this is to this, so as this is to that. That's correct. Therefore also the whole HK, that's this right across here, the whole line right across here, is to the whole KF. So as this is to this, so is this is to that. For as one of the antecedents is to one of the consequents, so are all the antecedents to all the consequents, which is by Euclid Book 5, proposition number 12. But as FK is to KE, as this is to this, so is CD to BD. Okay? Now let me repeat that for you. As this is to this, so is this is to this. That's by Euclid Book 5, proposition number 11. Therefore also, as this is to this, so is this is to that. Okay? But the square on CD, we take the length of CD, we turn it into a square, and that's this right here. It's commensurable with dB, the square on dB. This is commensurable with that. That's by Euclid Book 10, proposition number 36. Therefore, the square on HK, which is this, is also commensurable with the square on KF, which is this. That's by Euclid Book 6, proposition number 22, and by Euclid Book 10, proposition number 11. And as the square on HK is to the square on KF, so is HK, the line, is to KE. Since the three straight lines, HK, which is this, KF, which is this, and KE, which is that, are all proportional. That's by Euclid Book 5, definition number 9. Yeah, it's Euclid Book 5. It's Euclid Book 5, definition number 9. Therefore, HK, which is this whole line right across here, is commensurable with KE, which is the little tiny line. So that HE, which is this right across here, okay, is commensurable with EK, which is this. That's by Euclid Book 10, proposition number 15. Now, since the square on A, which is this, is equal to the rectangle EHBD, which is this, these are now equal in area. While the square on A is rational, therefore this rectangular area here is also rational. And it's going to be applied to the straight line BD. So we're going to apply this to that. Okay. Therefore, EH is rational. This line here, from here to here, this line is rational. And it's commensurable with BD. And that's by Euclid Book 10, Euclid Book 10, proposition number, looks like 20. Euclid Book 10, proposition number 20. So that EK, okay, what is EK? That's this right across here. Being commensurable with it is also rational and commensurable with BD. This is rational and it's commensurable with that. Since then, as CD is to BD, as this is to that, so is FK to KE. So is this is to that. As this is to this, so is this to that. Wow, CD and DB are straight lines commensurable in square only. Well, the only time that this line and this line are commensurable is when they are squared. Therefore, FK, which is this line right across here, and KE, which is this line right across here, the only time this line is commensurable with this one is if it's squared. This is by Euclid Book 10, proposition number 11. But KE is rational. That's a rational line. Therefore, FK is also a rational line. Therefore, FK and KE are rational straight lines. They are only commensurable in square. Therefore, EF is an apotome. Now we've established that this is an apotome. That's by Euclid Book 10, proposition number 73. Now the square on CD, that's this one right here, is greater than the square on DB, which is this one right here, either by the square on a straight line commensurable with CD or by the square on a straight line incommensurable with it. If then the square on CD is greater than the square on DB, by the square on a straight line commensurable with CD, the square on FK, which is this one right here, is also greater than the square on KE, which is this one right here. This is bigger than this. By the square on a straight line commensurable with FK, which is by Euclid Book 10, proposition number 14. And if CD, line CD right across here, is commensurable in length with the rational straight line set out, so also is FK. This is by Euclid Book 10, proposition number 11 and 12. If BD is so commensurable, if this is also commensurable, so also is KE. But if neither the straight line CD and DB is so commensurable, neither is the straight lines FK and KE is also. Okay. So, if this is not commensurable with this, then also this is not commensurable with that. But if the square on CD is greater than the square on DB, okay, so if this is greater than this, by the square on a straight line incommensurable with CD, then the square on FK, which is this one right here, is also greater than the square on KE, which is this one right here, by the square on a straight line incommensurable with FK, which is by Euclid Book 10, proposition number 14. And if CD is commensurable with the rational straight line set out, so is FK. And if BD is also commensurable, so is KE. But if neither the straight line CD or DB, so if neither this line or this line is so commensurable, neither the straight lines FK and KE are so that FE is an apotome. That's an apotome. The terms of which FK, KE are commensurable with the terms on CD, DB of the binomial straight line, and the same ratio, it has the same order as BC. Wow, oh wow. That was a long proof, don't you think? We only have 3 more proofs to finish, and then we're out of Euclid Book 10. Thank heavens. I don't think I can take any more proofs. Alright folks, I will tell you more in a future video, so I want you to stay tuned.